Announcements before we get started. Had an assignment due last night. We have an assignment due next week. I've helped a few people get started on that assignment, and it's turned some confusion into a path forward. So if you're in a similar boat, I am very happy to help. I received graded exams yesterday, so they are ready to go in my office. And since I said I would go over them tomorrow during class, I will still stick to that. But if you would like to stop by my office and see your score and take a quick look over it just to ease the concerns that you might have, I would be happy to share that with you to not delay that by an additional day. So feel free to stop by during office hours or sometime later this afternoon, and yeah, I can share a score and just overall statistics that I will share in class tomorrow as well. I can say that it went better than I thought, which is good.
Really? Talk about a surprise to hear.
I'm quite happy with the end result. So I'll talk more about it tomorrow. But again, if you're curious or if that makes you very much want to stop by, then you are welcome to do so. Great question. Slides for pseudocode for the sequence alignment going to be posted. Yes, that should be posted today. If it is not posted by this afternoon, send me any review, and I'll make sure to get those up as soon as I can. A few things to remember today. Other questions before we dive back into material?
I'll take.
All right, we'll go do that. Okay, so last time we were talking about greedy algorithms, we had a little bit of an introduction to the idea of a greedy algorithm. The basic idea was these are frequently problems that we can solve with dynamic programming. But if we can make a greedy assumption and we can prove that that greedy assumption always leads to the optimal solution, then we can end up with an even more efficient solution than if we stored and looked up subproblems. And that is very exciting. So we ended last class talking about this problem about a thief stealing from somewhere. And they have a certain amount of space or weight that they can carry. And they wanted to maximize the value of what they take away. So they're capable of carrying up to W pounds of loot. There are n items in the store, and the ith item is worth some amount of value, V sub I, as a weight, W sub I in pounds. So the question we're trying to optimize is to find the items the thieves should take to maximize what they take away. Were there any thoughts on this? So we asked kind of what would a greedy solution to this look like? And I kind of left things there for thinking about this in terms of what would that greedy solution look like. So we can either talk about it now if we're ready to talk about it, think about it for another minute or two, and then come back to it. But what would it look like to have a greedy solution to this problem? And then can we show either yes or no, this greedy solution will always work, or here is an instance where that greedy assumption would not work? I actually think a minute or two might not be enough. If you have paper, see if you can draw out something. Can you find an example of where a greedy solution would not be good? Or if going through some examples, you start to see a pattern, like there's always a best way to handle this, that would lead you to start to think maybe a greedy solution is good here, and we should figure out how that's going to work or how we could show that that assumption will always be good. Start with small problems. Don't make something where there are 10 items in the store, or there are 100 items in the store. Start with a very few number of items and see if you can come up with a counterexample, or if you can not come up with a counterexample and show that maybe we should look at this as a greedy problem.
It's valuable,
Just like in real life, we want the most money.
Yeah.
Except for me, I'm in the wrong field for that.
This actually does remind me of something from a while ago. I'll explain a little later, maybe, but.
What was that? Sorry? Like Ocean's 8? Yeah.
I was thinking Skyrim.
That's true. That's a good one to think about as well. If there's you have a certain amount of weight limit in an RPG, and you want to fill up your inventory with the most value that you can, given you have a limit to your inventory.
Yeah, perfect.
100 cheese wheels.
Yeah,
Absolutely.
this actually it doesn't just remind me of, let's see, Skyrim and Fortnite does that too, actually. But
If it's 100 cheese wheels, I don't know if it would make it to the store. They would just be consumed by me on the way to the store, and it wouldn't actually lead to any profit. Oh, sweet roll.
well, yeah, this actually reminds me of something else, actually. I used to work for FedEx Ground down in Auburn, actually, and we often like I was mainly a package handler, and like we spent our time loading numerous amounts of packages, like thousands of them into these trucks, and we were basically putting them and stacking them with how many just adapting how much they weighed and how much we could fit and how.
Yeah, this is a very similar kind of problem. I'm
Yeah.
directly onto that
We-
problem as well.
And we didn't even know which package they'd be coming next most of the time. At least I didn't. So I had to adapt.
Mhm.
Sure, we have plenty of protocol, but I was a little bit of a maverick there too.
Yeah,
May not be the most optimal solution, but I think I have a metric of how I problem check the versus problem.
let's hear it.
Yeah, so I was thinking about it less of like entries add on for that and like which is closest to like the highest value. I was kind of thinking of kind of more ratios of like weight to value.
Yeah,
And I was comparing off of that, like say we have like 3 items that like weigh 5 pounds, with each of them are value 10, which is a weight that is like 20 pounds, which is worth 30. I kind of did a quick math on it. That ratio is like 15 to 30 versus 20 to 30, which where 15 is like the 3 smaller items, so less weight
Right.
to load, so you can add more. So putting in terms of ratios, I want to choose the one with the smaller amount to that. So I can, so that's what I discovered.
that is the best grading approach we can take, is we want to look at value per weight. And then we would sort by value per weight and just start picking the best value per weight that we can get. Whether we can use this or not boils down to whether we can come up with a counterexample. If we applied that algorithm is there any way by applying that we could end up with a suboptimal answer? If the answer is no, then this is a great thing to do. But if the answer is yes, maybe there's something that we would want to think about. Yeah.
What about something like an old couch? You know, that would weigh a lot, but it's probably not gonna net you a lot of profit, say, but like something like maybe like a Rolex.
Yeah.
That's like the only thing I can think of where maybe.
Yeah, if we sorted by that ratio, then the Rolex would be way higher. It's cheap and it's expensive and light. And the couch is not, it's cheap and heavy. So it would be at the bottom of that list. So that would lead you to prioritizing the Rolex way before prioritizing the couch. But is there any way this can go wrong? That's the big question here. Is there a counterexample out there? Do the n items need to be a contiguous subset? I can think of a couple things that could mean. We do need to take full items, like we can't decide to bring in a chainsaw and cut the couch in half. That doesn't work so well. So we do have to take whole items. They're represented in an array and we choose them randomly. You could sort the array by this value to weight ratio. And then just start picking items from the most valuable per weight to the least valuable per weight until you run out of space. Yeah.
The only the only thing I could think of that wouldn't work is like if the ratio that you have for an item, like if an item's really heavy, but it's also really valuable, like maybe the ratio would depict like just how expensive the item was. So it'd be like lower on the list, but maybe just some of the items that are high on the list.
Like something like a statue.
Yeah.
Well, if the single item is more than you can carry in terms of weight, then you would not choose to carry that in general. Yeah.
I think I might have just misunderstood, because when I was going back to the ratios of like choosing optimal because on that works lower. I was thinking like a greedy approach would be just choose the most valuable item every time. That'd be a greedy approach, where optimize one versus would be this one. So what's suboptimal is where you're always choosing the one where it's always the most valuable, whereas optimal is choosing like a right ratio of weight value. So
Yeah.
you get more bang for your buck in terms of weights.
So this is an example of a problem where a greedy approach actually does not quite work, even though intuitively you would think that it would work. An example that we can use to visualize this is we have 50 pounds available to us. We only need 3 items in order to provide a counterexample. We can carry up to 50 pounds. There are 3 possible items: a 10-pound item selling for $60, a 20-pound item for $100, and a 30-pound item for $120. What is the optimal? What is optimal to put in our knapsack in this place? This is actually called the knapsack problem.
Maybe 1 and 2, but item 3 would be able to fit.
Yeah, if we do 1 and 2, then we can't fit 3. So if we break this down by value, by that value ratio, then item 1 is $6 per pound, item 2 is $5 per pound, and item 3 is $4 per pound. So you would see item 1, put item 1 in the knapsack. See item 2, put item 2 in the knapsack. See item 3 doesn't fit in the knapsack, terminate, and we profit $160. What is the optimal solution?
Item 2 and 3.
Items 2 and 3.
Yeah.
That gives us $220 instead of sorting it and going through that process. Does it make sense as deriving a counterexample like this as to why the intuitive greedy approach to this doesn't work?
That would take that.
What should we have done instead? Is there a different greedy approach that we could take other than the value to weight ratio?
There you go.
No, maybe not the.
Percent capacity to price? That's an
Yeah.
interesting concept. So we have 1/5 of our capacity for $60. The question is going to boil down to if we take a certain subset of items, when we choose a particular item, which items are we saying we can no longer fit? When we pick item 1, we can still pick items 2 and 3, but not the combination of items 2 and 3. When we pick item 2, you have to go deep down into this, selecting multiple items before you see the contradiction arise with what you can't fit in your knapsack anymore. So the fact that we need to start thinking about combinations of items should make you think that a greedy approach to this is not going to work no matter what we do. And that ends up being true. This is a problem that should be solved with dynamic programming, not with a greedy approach. But it's a very good intro to greedy because it shows you that your intuition can lie to you. Because frequently, people will see this and think that there is an obvious optimal approach to this, but you think about it a bit more in depth and you can find those counterexamples. You can find ways that it does not provide the optimal answer. So we can see what was optimal was 2 and 3, and any other combination that we could have picked is going to give us a worse answer. What if we could have an arbitrary number of each of these items? If this was a store with basically an infinite supply of items 1 and 2 and 3, would the greedy approach have worked then?
Yeah, you can just pick item 1 continuously.
A bunch of item 1?
Maybe, I don't know, 60 times 5, that's like $300, and that's decent. Actually, wait, no, this is one
What
of
if item 1 weren't available? We pick item 2, and then we pick item 2, and then we couldn't pick item 3? Or another item 2, would be better to pick item 2 and item 3 than item 2 and item 2?
That's yeah,
So it still wouldn't work.
no.
Okay? Question?
Yeah,
Thought?
I'm currently having a thought. Granted, if this were like an actual algorithm, it would take forever to actually process, but if you were to take, items and say, find them until they reach close to the size of the knapsack, and then use the, weight to value ratio on the combined, item, would that not get to be closer to a greedy algorithm?
It was probably closer to an approximation algorithm. I think you get very close to the optimal answer. My gut still tells me that I can come up with a counterexample to it, but you wouldn't have quite the level of issue that we have here. When we talk about approximation algorithms, if this were something that you wanted to put forward for actual implementation, you'd want to be able to place bounds on how bad can the answer be in the worst case. And so you'd be able to say, I can get to within plus or minus this of the optimal answer. But now we get to apply a linear time greedy algorithm for the entirety of the knapsack until we can just fit in a smaller subset of items left. And then when we go to dynamic programming from there, even though that's quadratic, that's going to be a much smaller n than it otherwise would have been. So the trade-off is that we get a significant increase in time at the detriment of we're going to have potentially a slightly suboptimal answer. But it doesn't take you quite as much time to process. If you're the thief and you didn't bring a computer with you, then maybe you want to apply an algorithm that doesn't take quadratic time. So you're not there in the morning when the owner walks into the store, still trying to figure out what to take. That's not going to go so well for you, thief. Sorry, the complexity of the problem was just so high that I had to stay here and optimize it. I realize I'll spend the rest of my life in jail at this point, but I should have thought of a more efficient algorithm before I walked into the store.
And I just quickly did the math on it, if we were to go with my idea, it would return the 160, which isn't right.
Yeah, so it would get you, if you were way more items and a way larger knapsack, then it would allow you to get closer to this problem, where you would be optimally handling 90% of the problem, 95% of the problem, and then the remaining bit of the problem, we might be substituting the 220 for a 160 at the very end of a problem. And we combine that with the value to weight ratio, come up with some more complicated score for an item. Maybe. My gut still tells me that there's going to be, it's either going to end up with the complexity, calculating that score and applying it, is going to be the equivalent of dynamic programming. Dynamic programming is basically doing the concept of that score, but it's keeping track of a recursive score. So I think you would be trading off time for correctness, regardless of what you do. The more complicated score that you can handle, the closer bounds you can get to the optimal answer. And then you can get the optimal answer if you have a quadratic algorithm. We're ready for problem 2, a very similar problem to this. Any other discussion points on the discrete knapsack problem? Okay, we're going to turn it into the continuous knapsack problem. So, exact same setup, you're still a thief, except now you bring your chainsaw. This poor owner, when they walk into the store in the morning, some of their items are just cut in half, cut in pieces. But the question here is, does this meaningfully change the problem? If we can take fractional items.
Well, lose their value.
Sorry?
Will they not lose their value?
They're going to be proportional to the size of the item in this case. So half of a Rolex is exactly half as valuable as a whole Rolex. Even though I don't know how it tells time, but who buys a Rolex to tell time anyway? I would argue with the same kind of person who would buy a Rolex. It's like I couldn't afford the whole thing, but I still wanted to look cool. So I've drawn half a Rolex on me, and the other half is a real half of a Rolex.
They'd probably see it as like a fashion statement.
Exactly. This is a computer scientist putting themselves in the position of a business person. This is why I would never fly as a business person. Question?
Yeah, is there an accrued time cost with like every time you do like?
Nope.
Weight it all, because I'm really debating just having them make infinite slices to an item and somehow find valid. But I don't know.
I mean, if we could just take fractional items, can we just do the same thing as last time, take the most valuable stuff and then the next most valuable and the next most valuable?
Yeah.
Till we're out of, maybe we still have space left, then we can just take part of the next most valuable.
Yep. In this case, a greedy approach will work. This changes everything. So now we're going to do exactly what was prescribed before. We're going to sort the items by value to weight ratio, which is exactly what we want. And we can take every item that fits in our knapsack until we find the next item that doesn't fit in our knapsack. And then we fill our knapsack with as much partial of that item as fits in the knapsack, and then we walk out the door. Very efficient. So we're going to take the 10 weight item, take the 20 weight item. The 30 weight item doesn't fit, but we can fit 2/3 of the 30 weight item. So we'll get 2/3 of the value out of the 30 weight item. And that improves on anything we could have done in the discrete knapsack problem. Instead of $180, sorry, it was $220. Instead of $220, we can get $240 by taking partial items. Is there any way the greedy approach produces a suboptimal solution? And in this case, nope.
If you had constants in this problem, would that be like revving up the chainsaw? Like the amount of time it took?
Yeah, if there was a cost, there might be a time cost. Or a noise cost. If anyone's walking by and wondering why a jewelry store sounds like there's a chainsaw happening inside, what's going on in there?
I'm sure the cameras won't see a thing.
Absolutely not. Assume this thief is doing this before cell phones and cameras exist. All right, so I wanna, yeah, question.
Screen approach still not work if you can take multiple of an item, because then you take all 5 of the 10 ones.
Which is the right answer.
Still,
It would work in that even though, let's say our knapsack, instead of being 50 pounds, is 45 pounds. So you take 4 copies of item 1 that has the best value, and then you would cut the next item 1 in half. And that would also work. That's a good point. But there would be no reason to consider anything other than the best value to weight ratio item. Every other item wouldn't exist as far as the thief is concerned if there could be more the item. So I want to tie this into reality a little bit. As nice as it is to role play the concept of a thief, it's very unlikely any of us are going to be doing that in the future. At least I hope so. So let's tie this back into something that is actually used in computer science. Has anyone heard of Huffman codes before? I think I accidentally slightly misanimated this slide in that there's something here before we should see it. That's okay, it doesn't spoil too much. But the idea of Huffman codes is this is going to be a lookup based on frequency. So we know when we made a binary search tree that we could insert, delete, or get in logarithmic time. But imagine that we want it to be even faster than that, not necessarily asymptotically, but we want there to be some kind of, we want the fastest average get that we can possibly have. In order to have the fastest get, we would want to know the frequency of queries of the different items, because it's not likely that every single item in our tree is going to be asked a get equally frequently. You can imagine that you're storing a binary search tree of maybe their references, so it ends up being kind of a tree map underneath the hood of dictionary words and their definitions. People look up words in the dictionary at very different rates, depending on the word. Some of them are more frequently queried than others. So how could we try to come up with an optimal tree that now we don't really care about how deep the tree is? We just care about the average query having the least time in order to get that query. Does that make sense as an optimization problem? The average query should take the fewest number of comparisons in order to get into the tree to find the answer to that. So based on that, the least frequent queries should be the deepest in the tree. The most frequent queries should be the shallowest in the tree.
Almost like the caching loop.
Yeah, but if you do this kind of like a linked list where the most frequent query is at the top and the least frequent query is at the bottom, that works, but we're not taking advantage of the tree structure where we can use a branching factor of up to 2 in order to kind of create that binary search. So Huffman codes are this exact idea of how to optimize, given that you know you have a list of items to be queried and you have a relative frequency. This could also be something like the frequency of a word in a document. And we want to be able to look up something like that in a structure. So we're going to imagine that we have n letters in an alphabet. We want to condense documents. Huffman codes are used to optimize, what's the word?
Yeah, let's see, optimize frequency of,
When you make a file smaller,
yeah. Yeah, optimize file size, right?
yeah. Yeah, so if you're trying to condense the file as much as possible into, yeah, compression, thank you. When you compress the file, you want the file size to be as small as possible. And so you can do that by coming up with the frequency of aspects in that, and you create a structure that stores only one copy of that, but makes it so that the time to compress and to decompress is going to be, it's going to be the smallest possible structure with the fastest possible time. So to do that, you can imagine instead of storing each character as a character requiring 8 bits, we could store each character based on the frequency it occurs and converting that character into a smaller representation. Something that is smaller than the required 8 bits to store a character in ASCII. So we want a binary search tree. Each character needs a unique code that identifies it. So here's an example down at the bottom. We have a file that the character F appears 5 times, the character E appears 9 times, C appears 12 times, B 13, D 16, and A 45. Given this, how could we construct a tree that tells us unique codes for each of these letters so that we could compress the file that has these characters with these frequencies into the smallest possible file? So we could allow character bit lengths to vary. Instead of everything being the same size, now some characters will be longer than others. But the idea is that when you read into the character, by the time you reach a particular point, you are guaranteed termination. This 3-character code represents A. This 7-character code represents F. What is the smallest possible way to do that? The best possible way to do that? And it turns out the approach is greedy. And you wouldn't necessarily intuitively see this as a greedy problem, but it's incredibly efficient to solve. So common letters have shorter representations, rarer letters have longer representations. How do we do it? So 6 characters in this alphabet with the following frequencies, or in this document. Let's look at how we could solve it. The approach, we're going to say, let's look at the 2 least frequently used nodes in a subtree. Then we're going to combine them. We're going to root those 2 nodes with a separate root that is the combination of those 2 values. Then we're going to reinsert as a node that subtree. So on the first iteration, we're going to take F and E. We're going to combine their frequencies together and make a root node 14 that has a left child F and a right child E. The left child is always going to represent bit 0, and the right child is always going to represent bit 1. This will make more sense as we make further steps in this process. But now there are 5 characters left. There's the C, there's the B, there's the F and E combination, there's the D, and there's the A. So of what remains, what are the 2 least frequently used nodes? C and B. We're going to combine those with a separate root. So now we have a 25 there representing C and B. C is that node's left child representing bit 0. B is that node's right child representing bit 1. And now there are only 4 nodes left to combine. Of the nodes that are here, which 2 have the least frequency?
14.
14 counts. 14 and D. So we're going to combine those with a new root that is the sum of those values, 30. The left child, representing a 0, gets us to the old 14 node. And the right child, as a 1, gets us to the leaf D. Continuing, which nodes have the least value? 25 and 30? Let's combine them. sum their values, that becomes the new root. One left, or two left at this point, we combine the A with the 55, and we get the complete tree. Is it balanced?
No,
Not at all, and in this case, it does not matter. It is not a binary search tree, it's just a binary tree. What this tells us, though, is it tells us how to create the strings for each of the associated letters. If you see the string 0, it immediately represents the character A. If you see the string 100, it represents the character C. So this allows us to concatenate these values together because each of these have a unique path from this new root to the end. There's never any ambiguity between which character we could be representing. To give you an example, here's a string. What character sequence does this string represent? Yeah?
AACD.
It is. It is AACD. Is there anything about the length of this string that tells us how many characters are in it? Nope. But we've gone from representing each of these characters as 8 bits to coming up with a very short representation, 8 total bits for 4 characters. The way we do it is we take this first 0, start at the root, and just track down from here. We get to the A. And since that's a leaf, we just immediately replace this 0 with the A. Restart back at the root. Start pathing from the root, we see a 0, that immediately goes to another A. Start back at the root, we start pathing 1, says go right, then go left, and then we are at a root, the C, so these 3 characters produce C. Then again, starting all the way back at the root, we go right, then right, then right, and that leads us to a leaf as well, and that maps to a D. There was never any ambiguity in this tree. We're just waiting until we get to a leaf. And when we get to a leaf, it tells us what the characters that we consumed, starting from the root, getting to that leaf, what that represents. And it turns out that this is the optimal decomposition based on this number of characters and these frequencies. This is the best way to compress this data. So it's a compression algorithm. It's used in practice. It works very well. But it relies on a beforehand analyzing the document, figuring out the frequency, building this table. Let's give you another example. What is this string?
awesome. One.
Yeah?
Yababa.
Yababa, I think that's right.
EABB.
Yeah, that's what I calculated looking at this real quick. I remember writing this, but obviously I don't remember what I had decided when I wrote this. So I had to quickly go verify it myself, but that's what I got as well. Let's go through the process. We go right from 100, taking us to 55, right from there to 30, left from there to 14, right from there to E. So these 4 characters all map to the single character E.
Oh,
Since we hit a root, we go back to, since we hit a leaf, we go back to the root. From 100, we go left and hit A. Already a leaf, so we're done. We go from the root again, right to 55, left to 25, right, and we're at a leaf, that's B. Starting again, we go right to 55, that's exactly what we just did, right to 55, left to 25, right to B. Starting back at the root again, just left takes us to the A. So we end up with, yeah, EBBA. Questions on how to read a Huffman code given a tree? Questions on how to construct a Huffman tree so that we can make these Huffman codes?
understand now.
So the next natural question I have for people is, what is the runtime of both constructing the tree and then creating the code for a string of size n? We have 5 characters maybe. Yeah,
You say construction 7, because the next terms where it defines between like going from the lowest value combining to like parent node there, and combine next and closest like lowest 7 operations penetrating total from the actual graph.
yeah,
And so then that's just to create, and it's not like a APL binary search tree where it's like longer than you get like more letters.
yeah.
But in terms of searching, I believe the depth of that tree is yeah, depth is 3, so
Yeah, so we start with n characters. There were 6 of them in this case. Constructing this was a 5-step process where we are consistently just building out the next combination. So it took us 5 steps, and it will always take n-1 steps to construct the tree. When we construct the tree, we're taking references. So we don't ever care about the depth of the tree during that construction. So it's a very fast construction. When we query something from there, what is the worst case for a query? Is there any guarantee about the maximum depth of this structure? In the big picture, is this closer to logarithmic, or is this closer to linear? Yeah.
I want to say linear.
In the absolute worst case, a query could be linear per character. What would it need to be in order for that to be linear? Like what would the associated frequencies have to be to create a linked list instead of a tree?
They don't get home.
So it can't be a linked list. I think that's important to see. When we combine the first 2 nodes, we're creating a 0 and a 1 here. So in the absolute worst case, we're creating a tree that when we combine the nodes, looks like that. And then when we combine, this looks like another node like that. And then this will combine and make another node like that, and combine and make another node like that. That is kind of the worst thing that we could do. What is the depth of this tree? Is this scales with proportion to the number of eventual leaves? It'd be the depth is again going to be n-1 because we get 2
Yeah.
leaves here in the last, but we add 1 leaf per construction, 1 leaf per level. So this leads us to an absolute worst case. And then what would have to be true about the associated characters in order for that to be the case? These would have to sum to be something that is less than that. So maybe we have 1 and 2, which gives us 3. And then this would have to be larger than 3, otherwise it would have been considered. So this is gonna have to be. Yeah, it's gonna be 4, bringing this to be 7. This has to be bigger than that.
Yeah. Okay, so let's see, that's like,
And so we see that we end up with a construction that when we end up doing queries into this table, if we look at the associated frequency that's necessary to create a tree structure like this, we are so frequently just having a structure that is length 1 here that it becomes logarithmic. Even though the depth of this tree is in the worst case linear, the average query to this is going to be logarithmic. So thinking about the worst case construction of the tree leads us to query what has to be true about the frequencies in order to construct that. And once we go about constructing that, we realize that the average query is back to logarithmic. And so the runtime of Huffman on n characters ends up being n log n, the n time to construct the tree, and then for each query, we're going to end up with a logarithmic time average query. And we can't even say worst case necessarily because the frequency tells us how frequent, if we're querying the entire document in order to compress it, we know those frequencies. So we're going to hit every one of those characters. It's not a proportion. You can't get unlucky. If this did represent something that you could query, like the construction of a database, then the worst case could be that you're always looking at the deepest node. But in that case, you wouldn't want to construct something quite like this anyway. It's more used for compression. So yeah, we can show that the greedy assumption optimally solves the problem. And it works very nicely. Questions on this greedy approach or why this works?
no, I don't think so. Wow, time goes by so fast.
The material is interesting, hopefully. Hopefully I've designed this to at least pique people's curiosity.
Plenty of it at least, I think.
So this is the end of what I anticipate covering with regards to greedy algorithms. The typical problem for this is just the knapsack problem as an introductory problem. Huffman code's presented as an application where this is actually used in practice, but greedy algorithms are actually very easy to construct and typically also to analyze. The hard part about greedy algorithms is always in the construction or proof that the greedy assumption leads to an optimal algorithm. That's a good question. How do we expand on this idea? So if we go back to kind of the greedy strategy or the greedy approach, kind of this slide right here, when you find an unknown problem and you think about starting to break it down into that recursive solution, what would a dynamic programming solution look like? You'll start asking yourself, is there an assumption that we can make that always produces the optimal answer, or that always breaks it down into a single subproblem that allows us to make that assumption? And a lot of this class is kind of theoretical and high level in that regard. Just because it's hard to give every example of when something is used, but so one thing that's going to be coming up, I can give a couple of further announcements at the very last couple of minutes of class. There will, in a couple of weeks, I believe, be an ICTC practice that ACM is going to be hosting. That's the International Collegiate Programming Competition that happens every November. Great thing to throw on your resume. This is something that you're around early next year. This is something that I highly recommend people consider. But a lot of those problems, they come from Caddis, which is a history of problems that have ever been given in these kinds of programming competitions. You'll find problems that you haven't seen before, and a lot of the more complicated questions will start requiring these kinds of techniques. And you know this because according to these problems, you have a limited amount of CPU time and memory to solve the problem. And so they'll give you a relatively complicated problem, and if you throw together a quadratic dynamic programming solution, it won't meet the time constraints of the problem. And the reason you fail at that problem is because you could have seen that there was a greedy approach that would take linear time instead of quadratic time. So Caddis is the site for that. I highly recommend people check it out. Super useful. And we'll have an actual competition in a couple of weeks. And at this point, you're studying the material that this will give you the idea of being able to see that. The other important announcement that I want to make is that there will be, you probably got an email about this yesterday, but a games exhibition for my game design students. And so that's happening Friday in 219 from 4 to 8. And you are all welcome to show up, bring people who also like to play games, and check out the games that my students developed. They're really cool. They put a lot of time and effort into it, and they would also like your feedback just about what worked, what didn't, how fun is just 4 weeks of time to make something that's supposed to be fun. There will be food, good times will be had, so I hope to see you there. See if there are concrete rules to apply, anything specific about a problem that is a clue that the greedy algorithm would be better than a dynamic programming for that. If you can break it down into a single subproblem instead of multiple subproblems, and that single subproblem has some assumption you can make. I'll see if I can come up with another example to kind of a, does the greedy approach work for this problem? And then you would be able to say, is there an assumption that I can make from this? But that's typically the best we have available. It's a tool in your tool belt that sometimes applies and sometimes doesn't. I will see you tomorrow for going over exams. Again, feel free to stop by if you would like to check out an exam score.
I'm sorry, what was the event you mentioned again?
It's the games exhibition, game design exhibition.
Oh,
Did we check out our source there?
Yes. Yeah. Head of my office and I can get it.
let's see, game design exhibition, where's that?
Why would-
Yeah. It's 11, yeah, absolutely.
Yeah, so where's the game design exhibition happening again?
It's in 219, the lab that's a couple doors down that way.
And wait, and what is it happening again?
Friday, 4 to 8 p.m.
Oh, okay, that's actually good to know. I suppose, well, what the heck?
Sit up there momentarily.
Yeah, sounds good.
Next Thursday, I'll get up there.
Sure, that works. Either, whichever you prefer. I'll be going there eventually anyway. Who wants to be next?
Will class be upstairs again, or was it gonna?
Yeah, this is just a 1-day thing. So, homework.